So we talked about how limits as you approach infinity or negative infinity are just like horizontal asymptotes. But where do these rules come from? How do we know when the denominator has a greater degree? It always approaches zero. Here's a quick way you could do it. Don't recommend doing this every time, but here's where that idea came from. It all starts from this limit where whenever we take the limit of something with a constant, any constant, divided by a variable that's getting infinitely large, that limit will go to zero. We're going to use that same idea to prove these rules here. And all you need to do is find the highest degree that's either in the numerator or denominator. For example 1, the highest degree is a second degree. Now this may seem weird, but if it's a second degree, that's the highest power, multiply both the top and bottom by 1 over x squared. So this whole thing equals 1. We're allowed to multiply by 1, but it's going to change the way it looks. It'll look like this. Pay close attention. I simplified each term. This will now be 4 over x, 1 over x squared, yada, yada, yada. And using that same limit that we know, any constant divided by a variable approaching infinity, this is going to wind up being 0 plus 0 over 3 plus 0 plus 0. Yep. It's no wonder that this becomes 0. And this works for each of them. You just have to find the highest degree term, and you can multiply by 1 over that highest degree term. And then multiplying through, you get the simplified versions. Remember, anytime you have a constant divided by a variable, or a variable squared or a variable cubed, that's going to approach 1. And by 1, I actually meant 0. That would approach 0. So that's how you can prove those horizontal asymptote rules, and that's how you can find the infinite limits, but you don't need to do a proof every time. However, you do need to pay attention for these tricks. Yeah, these examples are going to be a little bit trickier because did you know that sometimes there's more than one horizontal asymptote in any given function? What if there's an asymptote for one side of the graph and another one for the other side of the graph? Let's look at what could happen there. But first, remember, when you're dealing with these, look at the highest degree terms. What are they? Well, here's what they are. But how do you know what the degree term is when there's a square root? Well, if I take the square root of 4x squared, I'm going to get 2x. But because it's a square root, I'm going to get plus or minus 2x. Over here, I have the square root of x squared. Well, that's wonderful. That's easy. That's going to be x. Or is it negative x? Remember, a square root could have a positive or a negative answer. So how does that help us decide what it's going to be? Now it looks like I have 2 possibilities here. Really, there's only one for each of these, although there are 2 different asymptotes. Check this out. Isn't that telling me right there x is going to be a negative number? Really negative. It's so negative, it's approaching negative infinity. What we should be using here is our negative value. Likewise, as x approaches positive infinity, I'm looking at the positive value for that square root. That's showing me exactly what the graph's going to look like. So for each of these, if you have a square root, you look at whether x should be a positive or negative value, depending upon what x is approaching. That makes it so much easier to find these limits. You can find them now. The limits are shown there, and if you'd like to see a picture of what the graphs actually look like, please check out the notes on the portal. Look under Topics and Chapter 3. Finally, we have a couple more interesting little limits as you approach infinity. What happens if you have something that oscillates up and down, and it never stops? Does that ever approach one specific number? Or does it oscillate? You guessed it, it doesn't approach one number. Check out the notes to see what happens.